In class, we analyzed this function really carefully. Here I have a summary of everything that we discovered about f of x. We found that f of x has an infinite domain. We found the x and the y-intercept. We did a first derivative sign analysis. Within the first derivative, we found a critical value, and this was actually an official critical value because 4 2/3 is in the domain of the function. We came in, we found out that on the left of the critical value, the graph increases, so it increases in this interval, and here on the right of the critical value, the graph decreases, and we stated that right there. Then we did a second derivative analysis. There we found that a possible point of inflection happened at 4 1/3. And then with a quick check of the domain, we made it an official point of inflection. It was no longer a candidate, it was an actual place for a point of inflection. On the left of this value, we got that the second derivative was positive. That means concave up in this interval. And on the right part of 4 1/3, we got that the graph is concave down. So that's what we stated over here. Then we did an analysis on limit at positive infinity and limit at negative infinity. The limit at positive infinity ended up just being negative infinity. In fact, this should also be here. So we found there that the limit as x approaches positive infinity of the function ended up being negative infinity. So what this is telling us is that as x goes towards positive infinity, there is no horizontal asymptote. The graph is just going to come all the way down. But then as x approaches negative infinity, we approached a solid real number, a finite value. So this is telling us that on the left, as x approaches negative infinity, so in this direction right here, the x-axis, or the line y equals 0, is a horizontal asymptote. So on the right, we're going to see this graph come down, and on the left, we're going to see this graph approach a horizontal asymptote. Now, we were asked not to use a calculator when sketching this function. And if you notice, the local maximum point has a y value of e to the 14. Exponential functions, they grow very rapidly. E to the 14 is extremely large. I mean, if you pull your calculator and you approximate it, it's going to be a very, very large number. And so is e to the 13. But let's say that indeed the challenge is to do this without a calculator. Well, without a calculator, the best that you can do is just to do an approximation. You're not going to be able to have anything too accurately. So we're just going to go ahead on the graph and we're going to place these values, understanding that there is inaccuracy because we are not allowed to work with actual numbers to approximate it with a calculator. And then we're going to get a good enough representation of the graph. So this is what I have in mind. Let's go ahead and plot these points. So one of the points will be 4 1/3, and then the other one is going to be 4 2/3. So, and then the y-intercept is 0 and 15, and the x-intercept is 5, 0. Why don't we go 1, 2, 3, 4, and then 5 right here. So this is 4 and this is 5. Here we're going to have a point lying on the axis. And then at 4, no, let's plot the y-intercept. I mean, look at this. One of the y values is e to the 14. Huge value. We know how rapidly exponential functions grow. So 15 is minuscule. is tiny. That means that if we place it on the y-axis, it's going to be somewhere here, right here in the bottom, like very, very close to the x-axis, because e to the 14 is going to be high up here. So then let's sketch e to the 14, and this happens at 4 2/3. So let's say at 4 2/3, I'm going to use a different color. Let's say right here, e to the 14 will be placed, let's say somewhere here. So we're going to make this value right here, e to the 14. And then now let's sketch this one right here. This is going to be 2 times e to the 13. So it's going to be a little bit lower. And that's going to happen at 4 1/3. So let's say we place it somewhere here. So this is going to be 2 times e to the 13. And remember that this is exactly the point of inflection, the one, this point over here. And now what we're going to do is to now pay attention to everything else that we know about the graph. Remember that on the left of the point of inflection, and here is the point of inflection right here, our graph should be concave up. Then the concavity changes. And remember that at this point right here, at that particular point, I have a local maximum. So I should have something like this. And then again, concave up, concave down. The graph continues all the way down. And on the left, it approaches the x-axis. So that gives me a good sense of how to begin my sketch. Let's try that. We're going to have on the left, the graph is approaching the x-axis. It should go through my intercept, and then I'm going to try to climb all the way there, being as cautious as possible right here. Continuing up, and then moving down. I have to pass through the x-intercept, and then I know that the graph continues all the way down, and put an arrow here. Now here on the left, to indicate that we are approaching a horizontal asymptote, let's put an arrow there as well. Now I can go ahead and erase these yellow lines. I don't need that. That was only an initial guide that I wanted to have. Now that I have pretty much my sketch over here, I can easily determine the range of this graph. I always like to leave the range for the end because at the very end, when you have the figure in front of you, it is a lot easier to determine. So in this case, we will say that the range will go up to the highest value. The highest value, if you notice, is exactly the local maximum. In fact, now we know more. Now we know that this is not just simply a local maximum. This is an absolute maximum. An absolute maximum. And that's because the graph is increasing from left to right. And then on the right, the graph decreases. So then as it increases and increases, it reaches a maximum, and then it goes down, and it never comes back up. It continues going back down. So I know that this one over here becomes the highest y value. So then the range will be practically everything from negative infinity all the way to e to the 14. That becomes the range.